we've already introduced the idea of acids. There's many different definitions of an acid, and the definitions are all operational. If a tree falls in the forest kind of situations. Acids and base, those are behaviors of a material. That means that we observe how they behave under a certain set of situations. It acts as an acid, it acts as a base. When we describe something as an acid or a base, typically what we're doing is actually we're describing it as that under these types of conditions it has this type of behavior. So there are many different definitions. The simplest, and the one we're probably the most familiar with, is this Arrhenius definition of what an acid is. The Arrhenius acids we all are familiar with. They have some sort of material that releases H plus in solution. Our familiar acids are things like HCl, which in water will release H plus and the chloride ion. All right, so these fit the behavior of things that we know: HCl, H2SO4, etc., etc. These all behave as acids. The Arrhenius bases, on the other hand, in the Arrhenius definition, usually these are things like metal hydroxides that release hydroxide ions. And this would be something like sodium hydroxide. But this is a very limited definition. These are all aqueous solutions that in solution these materials will dissolve to produce aqueous ions. It turns out that H plus doesn't exist. It doesn't exist in aqueous solutions. More often than not, what we're talking about for H plus is the H3O plus ion. That is a water molecule that has picked up an extra proton. So a more inclusive definition are what we call Bronsted acids and bases. So the Bronsted acids, we should think of these in the presence of water rather than just being the media. They are actually one of the reactants. They accept a proton to form H3O plus plus X minus. Now if we squint our eyes, we'll notice that these two are very similar in their behavior except the water is an active player. A Bronsted acid donates an H plus. So this would be our Bronsted acid acting as an acid to donate the proton to the H2O plus. Now, a Bronsted base then is anything that accepts a proton. And so, in this case, this would be the base. The water is acting as a base. Now, what we really then care about is how much H3O plus is created in these systems. Acids create lots of H3O plus, bases don't. Right? Now, we can sort of fit this Arrhenius definition if we think about something like OH minus. It will react with HCl to produce H2O and Cl minus. Here we have the hydroxide accepting a proton. All right, so this one is acting as the base, with the HCl acting as an acid. If we can identify which one is the acid, by default, the other one has to be the base. If we look which one is donating the proton, and so what we have to do is we have to look at both. We have to look at both the starting material and how it relates to the products. All right. So how does the starting material, we have it as an extra proton, we see that it's lost an H plus to form the Cl minus. And so this is the material that is giving up the H plus, it is donating the H plus to something else. So that makes it the acid. Well, what about equilibrium? These reactions often are equilibrium, and so we can think about them in terms of equilibrium ideas, and where this material is acting as the acid and this one is acting as the base. If we look at it from this direction, we see that the HX is acting as the acid, the H2O is acting as the base. But if we look at it from the opposite direction, what we see is that the H3O plus, going backwards, would give up its proton to the X minus. And so in this case, we would see that the X minus is acting as a base, and the H3O plus is acting as an acid. So when we have an acid-base pair in a chemical reaction, in this case we're talking about the HX, we see that the acid liberates its proton to make the X minus, which is now a base. It can act as a base. Again, acid and base are behaviors. So we consider this relationship. We have an acid associated with it's what's called a conjugate base. And the acid, when it becomes deprotonated, forms the conjugate base. The base, when it gains a proton, forms the conjugate acid. So this conjugate acid-base pair is a fact out of all these behaviors. And so we can actually predict. So let's take a look at HCl. Let's say predict the conjugate acid. What's the conjugate acid of HCl? The difference between a conjugate acid and a conjugate base is one proton. A conjugate acid has an extra proton. So the conjugate acid of HCl would be H2Cl+, where it's gained a proton. The conjugate base, so what's the conjugate acid of H2O? That would be H3O+. The conjugate acid of Cl-, that would be HCl. Notice it's gained an H+, it starts as a Cl-, therefore the positive negatives can't. So we could also do the same thing for a conjugate base. Let's predict the conjugate base of HCl. Conjugate bases are the materials that have lost one proton. So if you take HCl and you subtract out a proton, that is Cl-. Sorry, I keep calling H+ the proton. All right. H+ is just a naked proton, but it's not the proton in the atomic sense, it's the proton in the molecular sense. The conjugate base of H2O, it's lost OH-. Now, this would represent a conjugate acid conjugate base pair. These two. Not this conjugate acid. Not these two. These aren't related. The conjugate acid is always with respect to one other thing. And the conjugate base of Cl-, well, there wouldn't be one, because you can't lose any more protons. It's always the loss of gain of one proton. So what would be the conjugate base of H2SO4? Yeah, think about it. Hit pause if you think about it. Well, the conjugate base would be loss of one proton, HSO4-. All of these bits and pieces are important. Of course, you're not going to go to the lab and get HSO4. You're going to get NaHSO4. So both of these, while this would be the ionic form, this would represent one of the conjugate bases of but you could also think of almost any salt that would meet that requirement. In solution, it would release that. the conjugate acid of H2SO4 would be H3SO4+. Now, when dealing with solutions of acids and bases, one of the things we care about is Kw. If you remember, Kw is the is the equilibrium associated with the dissociation of water to H2O, forming OH minus plus H3O plus, where one of the water molecules transfers its proton to the other to generate OH minus and H3O plus. This equilibrium is in effect. Kw is almost always equals 1 times 10 to the negative 14th at standard temperature and pressure, and for all intent and purposes it fluctuates only a little around those particular values, 1 times 10 to the minus 14th. You should memorize this. It's very handy. It comes in handy all the time. And associate that with the equilibrium constant H3O plus times OH minus, meaning that the H3O plus and the OH minus concentration are fixed based upon that behavior. And if you know one, we know the other. Now, associated with this, when you deal with acid and bases, is this concept of pH. All right? pH is one way of representing, it's related, it's not the same, it's related to the H3O plus concentration. pH is a way of representing the H3O plus concentration. It's not exactly the same. The pH of something is defined as being equal to -1 times the log of the H3O plus concentration. Now, on your calculator, depending on which calculator you have, you would enter this a number of different ways. On these style calculators, usually the way you do it, you enter the H3O plus concentration first, and then you hit the log button, and then you just take the negative of it. You just flip the sign, either in your head or on the calculator. This allows us to interrelate the pH to the hydronium ion concentration. Usually the way this works is, given H3O plus, we take the log of it, flip the sign, and that will equal the pH. So H3O plus to pH, we usually use that method. Going backwards, given pH, we use a modified form of this. 10 raised to the negative pH will equal the H3O plus concentration. So in this case, we're going to start using our 10 to the x key on our calculator. We enter the pH, and we plug it into our calculator, and we get the negative log. So for instance, if the pH was equal to 8.347, and again, when dealing with logs, these are the significant digits, 8.347, we take the negative of that number, and we raise that 10 to the x, and you get H3O plus will be equal to 4.5 times, 4.50 times 10 to the negative 9th. And so figure out that aspect of your calculator. So what that allows us to do is quickly interrate H3O plus and pH. We already know, though, that H3O plus is intimately tied to OH minus via Kw. 10 to the negative 14th is equal to H3O plus times OH minus. And so if we know one of them, we can rearrange and solve for the other. What's not so obvious is that we can also look at POH, which, like which like the pH, that would be equal to negative log of the OH minus concentration. Let's look at our example where our H3O plus concentration was equal to 4.50 times 10 to the negative 9th, and we wanted to know what the OH minus concentration was. Well, we would use this equation. We'd plug in our H3O plus, rearrange and solve. 10 to the negative 14th divided by H3O plus concentration equals our OH minus concentration, or 10 to the negative 14th divided by 4.5 times 10 to the negative 9th. It's equal to 2.222 times 10 to the negative 6th is equal to the OH minus concentration. If we wanted to find what the POH is, we would plug that value into our equation, negative log of that. So we take the log of that number. It's equal to 5.653 times 10, 5.653. And that would be equal to the POH concentration. Sorry, the POH. What's not 100% obvious is there's another relationship. It turns out that 14 is equal to POH plus pH. So if we know the POH, we can use it to find the pH, and vice versa. So if we just plug this value in, we can say, what is the pH when the POH is equal to 5.365, 5.653. And so we take, we find that the pH would be equal to 3.4, 8.346, which, if you were paying attention, was the value we used to start this whole calculation. All right, take-home message. Given any one value, given pH, POH, H3O plus, or OH minus, you should be able to calculate any of the other ones, which is basically gives you, 12 different calculations. So let's take a look at this. Let's if you know H3O plus, you can use it to obtain pH, because negative log of H3O plus will equal pH. And vice versa, if you know pH, you can figure out H3O plus. H3O plus, 10 to the negative pH, will equal H3O plus. Given pH, we know that we can use it to figure out POH, because we know that 14 is equal to pH plus POH, and vice versa. Basically just subtraction. And we can use POH to figure out OH minus, we can use POH to figure out OH minus, because we know 10 to the negative POH will equal OH minus. And we can use OH minus, negative log of the OH minus will equal POH. And lastly, we can relate H3O plus to Kw, because Kw is equal to H3O plus times OH minus. If we know one of them, we plug it in, rearrange, and solve for the other. So there you go. All right. Given any one of these, you should be able to reproduce the others. And I mean fast. This is a 2-minute calculation. Given pH, you should give me POH, H3O plus, and OH minus. Given any one of them, usually the way I do it, if you're lucky, if you have H3O plus, I usually go straight to pH, and then from pH, it's just subtraction to get POH, and then it's a real quick flip and exponent to give us OH minus. This should take 2 minutes. I would say a minute if you're fast. So that's what your goal is. Start to get this down to 2 minutes. 2 minutes to do 3 calculations. So let's practice, okay? What is the pH, POH, and OH minus concentration for a solution that is 0.035 molar H3O plus. Start your timers, go! So first is negative log of the H3O plus concentration will equal pH 0.035, negative log of 0.035 molar is equal to 1.456. So this will be the pH, and then we can subtract that. 14 minus pH will equal POH. In this case, plug that value in. This will give us a POH is equal to 12.54, and 10 raised to the negative POH will equal the H3O plus, sorry, the OH minus concentration, equal to 2.857 times 10 to the negative 13th. And if we did it right, the log of that should be 12.45, which it is, and we should be able to get those values. And we can check that by dividing this by 1 exponent 14. 1 over x gives us 3.5 times 10 to the negative 2 as our H3O plus concentration, which was our starting condition. All right, done.